Okay, hey everybody. I wanted to make this video because we kind of ran out of time on our last class period to work on this pre-lab activity, this lab prep activity for lab number 2. So we talked about the elements that are found in brass, copper, and zinc. Sometimes we get a little bit of iron in there, some other elements in trace amounts. But copper and zinc, major components. So we wrote these equations, and I'm not sure if this is showing up big enough. Let me zoom in just a little bit so that you can see a little bit better. Okay, so we've got our copper and our nitric acid react to form copper nitrate, nitrogen dioxide gas, which is a kind of an orange toxic gas. So we will be doing this in the fume hood, and water. And the zinc dissolves into the nitric acid as well, reacts with it, forming zinc nitrate, nitrogen dioxide, and water. So when we are doing this lab next week, we're going to be putting actual brass things into nitric acid to dissolve the metals. Okay, dissolve, not really dissolving them, reacting them and turning them to ionic compounds that are then dissolved. Okay, these are single replacement reactions, and our goal is to figure out what percentage of the brass was copper. That's our goal. Okay, so when we're looking at those solutions, copper nitrate, one of those products of the dissolving in nitric acid up here, is going to be blue in color. Zinc nitrate is colorless. Now, if there are other trace amounts of elements, those will have some color as well. So we get to this question number 5. For the solutions that have color as a class, we're going to run spectrophotometric analysis to determine the wavelengths that these solutions are absorbing. So I'm going to actually show you what that was supposed to look like right now. So I've got hopefully you can see the screen now that shows our spectrum of colors here. And I have calibrated the instrument with a blank cuvette, so with distilled water in it. And what I'm going to do is I'm going to collect wavelengths for copper, zinc, and then I'm going to do copper, zinc, and I'm going to do iron as well. Okay, so I'm going to first do copper. And if we look at this collection, I'm going to just, okay. We can see this crazy range of absorbencies, okay? But the highest absorbance is up here. And if I hover my little mouse over the highest part of the curve here, it's around, 810, 813, somewhere in here, okay? It's a lot of little zigzaggy pieces here. But what I'm going to do is I'm going to take the highest visible light. So the end of our visible light spectrum right here is that 780. And that's why in the pre-lab, when we're working here, for this one, we're going to say 780 would be a really ideal wavelength. We're going to work with visible light spectrum colors, okay? So it doesn't absorb this range very well. It definitely doesn't absorb, below 415. There's a little tiny peak here, but still in comparison, these wavelengths are absorbing, close to around half of what we're absorbing at our peak. Okay, so that's where we were getting that range. So in number 5, when we look over here, let me see if I can switch back quickly. For the copper nitrate solution, copper 2 nitrate to be specific, the range absorbed well is going to be anything basically over 750 nanometers. I'm not sure what we wrote in class, but over 750, absolutely absorbing well. Okay, the range not absorbed well would be below 700 nanometers. And again, I'm not sure what exactly we wrote last time. But that's kind of what we're seeing when we're looking at our screen. So let me get back to our colorful screen so you can see that again. Okay, so here we're absorbing well. If we're looking at this, about 750 right here is where we start to really get up here, and that's going to be a very good absorbance. But if we're looking below 700, all of it stays below this point. Okay, so we're all below 0.6 absorbance, around 700 nanometers. Okay, so now I'm going to switch this out, and I'm going to put the zinc nitrate in there. Now remember, our zinc nitrate is colorless. So we're going to do our collection, and this time I'm going to store it so we can still see the line for the copper nitrate. Okay, So I'm going to stop my collection here. We see we have a little tiny bit of absorption here, but I wouldn't say zinc nitrate absorbs well anywhere, okay? Because even this is less than 1/10 on the absorbance scale, okay? So when we switch back to the pre-lab sheet, okay, if we're looking at zinc nitrate, nowhere. It doesn't absorb anything well, and the range not absorbed is 0 to 900, okay? So when we're looking at the scale, that's what we're going to get. Now I'm going to do one more element here. I'm going to do iron nitrate, and I was trying to make all this red here, but our iron nitrate, it's going to be an iron 3 nitrate. Okay, we're going to test that one, and then we'll come back and we will record what that absorbs well and what it doesn't. So let me switch that out here. Okay, so collect, keep that copper line visible. Okay, all right. So here's our iron nitrate curve, this green line here. And if you look at this one, it is absorbing super well in these purple wavelengths, right? So I would say anything below, anything below, where are we here? 440. So 385 to 440, it's absorbing super well. And then outside of that range, it's not absorbing well at all. So we can do that. So 385 to 440, switching back over here, 385 to 440 nanometers. It absorbs really well, but it doesn't absorb outside of that range. Okay. And it's important when you have a mixture of colorful things that you do test each one, because if we were to pick a wavelength that both copper and iron absorbed well, then we would be testing for both of those things. But what we want to choose is a wavelength where I'm getting really high absorbance for the thing that I'm testing for. I'm getting really high absorbance for copper, and I'm getting no absorbance for nitrate or anything else in my solution. That way I know that all of the absorbance that I'm measuring is due to the copper. And then we can use Beer's law to figure out how much copper was in our sample after we test its absorbance, okay? Okay, I'm gonna go back to that prep lab activity and talk about these other questions. And just so that you have some clarity here. Okay, so 6, if we were testing a sample of brass for copper, what specific wavelength might be a good choice? Okay, again, I would like to stick to the visible light wavelengths. And so that high end of the visible light wavelength was 780 nanometers, and that's where we got that number. Remember, the peak for copper was around 815, 805, somewhere in there, but 780 was the edge of our visible spectrum. So we're going to stick with that. Okay, the highest absorbance in the visible spectrum. Okay, that way, if it's extra sunny in here the day that we do the lab, we're not affecting it as much. Okay, okay. 7, if a 1.00 gram sample of brass is added to a solution of nitric acid, what is the minimum volume of 6 molar nitric acid needed to ensure that all of the atoms of the brass react, assuming 65% copper and 35% zinc? So this problem is pretty complicated here. We're going to take that 1 gram sample, 65% of it is copper, 35% of it is zinc. So this is going to be 2 different stoichiometry problems. And I'm actually going to get down to a new page here to give myself some space to show this. And I'm going to insert a little table so I can show my factor label steps. I'm not sure how many boxes I'm going to need here, but okay, I'm going to start with 0.65 grams of copper. I don't need that spelled out. Okay, grams of copper. Okay, and then I know 1 mole of copper is 63.5 grams of copper. If I'm remembering that right. Let me grab my periodic table. Okay. All right. Then remember, this is stoichiometry. So when we go over here, we need to get moles of copper to cancel, and we are going to look up here at our equation. For every 1 mole of copper, and we're trying to figure out how much nitric acid we're going to be using, we need 4 moles of nitric acid to dissolve that mole of copper. So 1 mole of copper will react with 4 moles of HNO3. Okay, scooch this over. Okay, so now I've got moles of HNO3. I'm trying to get to volume. Well, remember, capital M, molar, means moles per liter. So I've got 6 moles of HNO3 in every 1 liter of HNO3. Okay. And I'm not going to need all of these here. This is my last step. Let me just delete these. And we know that there are 1,000 milliliters in 1 liter. Okay, so we can get the volume of nitric acid that we need using this setup for the copper. But remember, we also have some zinc in there. We have 35% zinc. So I'm going to do another problem for the zinc. Okay, so insert 5 columns here. Okay, so, but not 0.65 grams. The zinc was only 35%, so 0.35 grams of zinc. 1 mole of zinc weighs 65.4 grams. Again, 1 mole of zinc will need 4 moles of HNO3. And then we can finish the problem with these same pieces here. Okay. So then you can calculate out how many milliliters of nitric acid you would need to dissolve that entire 1 gram sample. Okay. All right. If the brass was 65% copper, how many moles of copper would you expect to have in your 1 gram sample? Well, 65 grams of copper, there's 0.65 grams of copper in the 65%. 1 mole is 63.5 grams. That piece right there is going to be the same for our answer here. Okay, so you're going to just calculate out the moles. Number 9, if the solution produced in the reaction with nitric acid is then diluted to 100 milliliters, what will the molar concentration of the copper ions be? Okay, so break that down a little bit. Molar concentration means moles per liter. Well, up here, you just calculated the moles. So you take that answer down here, you're going to divide that by the number of liters for your solution. So whatever your N moles of copper divided by 0.100 liters is going to equal your molarity, is going to equal your molarity of copper. And so you can just fill that in here, okay? So I hope that makes sense. And I'm going to just talk about the lab a little bit more so that you're prepared to do the lab. So that was our lab prep. Let me do a new share again. Okay, so you can see our objective. Again, what you're going to do is figure out the percent copper in a sample of brass. In order to do that, you have to know how much your sample of brass weighs. You have to react the entire sample with nitric acid to turn all of those ions or all those metal atoms into metal ions in solution. Then you're going to dilute your resulting solution to 100 milliliters and test its absorbance. Okay. Now we can use absorbance to find concentration because of Beer's law. So remember, that's going to be one of your equations. When I talk about your equations here, which equations you're going to be using, you're going to be using Beer's law. So absorbency equals epsilon BC, epsilon being the molar absorptivity, B is the path length, C is the concentration. Okay, we're going to make a Beer's law graph for copper nitrate so that you can use your graph to determine the concentration by using the linear equation that you're going to create from your graph. So you're going to need to know molarity equations. So molarity equals moles per liter. You're going to need M1V1 equals M2V2, because if your solution, after you're done dissolving your brass, if it's too dark, if it's absorbing too much light, remember, we're going to have to dilute it in order to make it fit into our Beer's law curve and have its absorbance within the around 1 range as a maximum, okay? You're also going to be doing some dilutions. So as you're dissolving your brass sample, you're going to take powdered crystalline copper nitrate, and you're going to make solutions. Remember, like we did in a class as a group with the food coloring, you're going to create a stock solution for yourself where its absorbance is somewhere around 1, maybe 1.2, somewhere in there, okay? Then you're going to dilute it in several dilutions so that you can create that line of absorbance versus concentration that we got for our blue food coloring. You're going to do that for yourself. Once you have that line, hopefully your brass will be all the way dissolved. You'll be able to dilute the resulting solution, test its absorbance. Maybe you might have to dilute it again, test its absorbance again, and then use math to back calculate what the concentration of your copper was in your brass sample. So these are the things you're going to need. Again, you're first going to be dissolving your brass sample into nitric acid. While you're waiting, you're going to create a bunch of different dilutions of copper nitrate. You have to create your own stock. You'll just kind of mix copper nitrate with water until you get to an absorbance of about 1, and then slowly dilute that and keep testing its absorbance to create your Beer's law line, where you have absorbance on the y-axis and you have molarity concentration on the x-axis. Then, after you've gotten your curve, your metal is completely dissolved, you dilute your metal solution, you're going to measure its absorbance. Hopefully it's within the 0 to 1 range, but if it's too high, you'll dilute it, measure it again, and then you'll have an extra math step to back calculate how much copper was in that brass. So we got a lot of things. Your dilutions, you get to choose what your dilutions are. You could do, your stock is your 100% solution, and then you can go in 80%, 60%, 40%, 20%, and then 0% with your distilled water. That's kind of what I would suggest, but you can choose any combination of dilutions that you want in order to bring this down and create your Beer's law curve, okay? Again, wavelength used to test the absorbance, we just talked about that in the lab prep. That's going to be our 780 nanometers. And then the conclusion piece hopefully will make more sense now that I've talked about this. So hopefully this is helpful. And if I'm not in class with you, I will answer all the questions that we have when we do the actual lab on lab day. I will be there for lab day. But if you have any further questions, please don't hesitate to email me. So thank you very much for tuning in. And I will see you guys the next time that we are in class together. Thanks, everybody. Bye.